All right, good. Well, last time we talked about basic definitions of fluid mechanics, of fluids, solids. We talked about dimensional homogeneity. We mentioned the fact that if you want to be able to add terms of an equation together, then they have to be dimensionally homogeneous. You can't add apples to oranges. So in the Bernoulli equation, all the terms that we looked at happen to be units of length, if you worked out what the units were. And we talked about how you could actually do those calculations from first principles. So this is good. This is a big fat pen, I guess. I don't like that. This equals constant. We talked about some fluid properties, especially in general about viscosity and density as an arbiter of whether fluids were liquids or gases. And we talked about the ideal gas law. We skipped over this, but certainly you know this, that mass is equal to density times the volume. We use these standard terms, getting just used to the terms that we'll use. We'll use the same units throughout, and the book uses the same units as we'll talk about here if you've decided to buy the book. Weight, so mass is invariant of what planet you're on. A kilogram is a kilogram whether you're on the moon or on the Earth, but the weight of that component is multiplied by the local gravitational acceleration. So the mass times gravity gives you weight. And so we'll use that. We talked about the ideal gas law. You should remember that both pressures and temperatures for that law are always in absolute magnitudes, not gauge pressures, not Celsius, but Kelvin or Rankine, depending on the unit system you're using. And so you should remember that. And we also talked, I guess, in addition to viscosity and density, we talked about compressibility. And so this actually, what's written here is the reciprocal of compressibility. It's modulus, which we'll call the volumetric modulus, which really just says the propensity of a fluid for compression. If the modulus is stiff, it's like water. You try and compress it, you have to apply big pressure to be able to get a small volume change or a given volume change. If it's a gas inside a balloon, you only have to apply a relatively small pressure to get a relatively small volume change. And we can define it in terms of this, etc. So those are the things that we talked about last time. So it may seem a little esoteric that we talked about compressibility and what it means, but it actually turns out to be important in terms of talking about wave speeds, which we'll talk about first. And unrelated to that, we'll talk about viscosity in a more with more depth. Talk about phase diagrams, and we'll talk about interfacial tension or surface tension. And we won't use a venometer. Maybe we'll talk about a venometer. A venometer is something you can tell what the alcohol content of your beer is when you go down to the Skeller or wherever the place to go these days is. Okay, so those are the things we'll talk about. So wave speeds first. Wave speeds come in a variety of flavors. We talked last time about the fact that when I'm talking to you, not the amplitude of what you hear, which is due to attenuation, but the timing of what you hear is transmitted from me across the room to you, the same as sonic boom of an airplane. And so the compressional wave is something that transits a medium, and it could be a fluid, such as air, which we're sitting in now, or if you try and speak underwater, in a liquid, but it could also be in a solid. And so the reason that I pulled up on the BBC homepage, but didn't show it, the Apennine earthquake in Italy, which has now taken 270 or so lives, is that earthquakes are basically a manifestation of the seismic transmission of energy in a solid instead of in a fluid, which is what we're doing now in terms of you hearing me. It doesn't hurt you too much. It might hurt you a little bit listening to me. I apologize for that, but it certainly doesn't have any really strong physical impact on you. And so we can link these together in terms of the ideas of wave speeds, which occur both within solids and fluids. And the compressional wave we can look at in thinking as, well, I don't want to go into too much detail. This is the bulk modulus. This is what we have called E sub V, which is the compressibility of an all-around pressure on a solid or a liquid or a gas, solid or a fluid. And this is referred to as the shear modulus. And so they are in response to different wave types. And so the best way to explain these two wave types is that the compressional modulus is the same as if you look at a series of railroad cars. You hit the end car, and that energy is transmitted up the series of other railroad cars, boom, 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 to the front. But the particles of the rail car don't physically go from the front back to the front. It's just the energy that's transmitted. And so that's exactly what happens in wave transport. Shear modulus would be the kind of wave that if you take a skipping rope not a very good analogy for the P wave because you can't compress the skipping rope and the thing will, I guess you could a slinky. But if you take a slinky and you just have someone holding one end and move it, you'll get this sine wave moving along it. And that's the shear wave. And so in earthquakes, usually there's the fastest moving wave is the compressional wave. And the slower moving wave is a shear wave, maybe by a factor of 2. Compressional wave is the one that hits first. The shear wave is the one that damages all the buildings because it distorts buildings on their it's much larger in magnitude, and it distorts buildings on their foundations, and that's the one that does the damage. And so in water, the shear modulus is essentially 0. Or gas, sorry. Why water? In a fluid, shear modulus goes to 0. So there is no shear wave that's transmitted in fluids. But as a consequence of that, that makes this relationship what we've called EV over density square root. And so if you look at this for rocks, the modulus of a rock is something like EV is equal to 10 to the 10 pascals. You can look it up. I just know that because I work with rocks. And the density of rocks are something like something of the order of 2,700 kilograms. Say 2,000, it's more than 2,000, it's probably 2,700 kilograms per meter cubed. So if you make the ratio of those, I'm just going to make it 2 times 10 to the 10, divided by 2 times 10 to the 3, just because I like things to be easy. Then that's approximately the wave speed, the P wave speed, which would be equal to what? 10 to the 10 divided by 10 to the 3, which is 10 to the 7, which is 10 times 10 to the 6, square root. And square root of 10 to the 6 is about 10 to the 3. This is about 3,000 meters a second, which is about right. Just because I know what the wave speeds are before I started. Never do a calculation in class unless you know the answer, I guess. So that's the speed for fluid. This isn't a very good chair. I keep on sinking, and I don't think it's because I'm too heavy. Well, maybe it is. So if you look at the wave speed for water, what would those numbers be for water? Any idea? We said last time. We said that the modulus of water is pretty close to that of rock, surprisingly. It's of the order of 2 GPa. So it'd be 2 times 10 to the 10. It would be, the density of water is 1 times 10 to the 3. And so this is of the order of, again, 2 times 10 to the 7, which is the same as 20 times 10 to the 6 square root, which is the same as square root, was that 4? (4,000 meters a second), which is high. But anyway, it's fine. But the bottom line is it's more of the order of 1,000 meters per second. So I'm not sure what I've done wrong. Yeah, maybe no 2. Oh yeah, 2 times 10 to the 6. It's 2 gigapascals, not 20 gigapascals. Yeah, go ahead. Can you speak up, please?
4 and 3. What does that mean when I say
Oh, 4/3. It's just a multiplier, yeah. So if this term goes to 0, then this also doesn't matter as well.
So that's like an exponent?
No, it's a fraction. 4/3 times. So, yeah, fine.
Just to be clear, you're using the shear wave equation.
I am using this equation with this equal to 0. I'm using this equation right here, because the shear modulus in a fluid is equal to 0. And I just used it by substitution here. So the point is that the acoustic velocity, this shouldn't be 4,000, it should be about 1,000 meters a second. You can check it, what I've done wrong. So that's the speed at which sound would travel if you were talking to someone underwater. If you look at the speed of transmission in air, you can use this same expression, and I guess we can do it for air. And what would that be? If we use it for air, then we know that EV is equal to, the compressional wave is equal to this. What are the magnitudes of those components? We talked about modulus last time. What's the modulus of air? What did we say about last time? We said it's equal to the pressure from the ideal gas law. Pressure in here is what? .1 of a kPa, or 14.7 psi. So it's 10 to the 5 pascals. So this would be 10 to the 5 newtons per meter squared. Density would be what? Density of air at room temperature, about 1 kilogram per meter cubed, square root. And if we look at what the magnitude of that would be, this would be 10 times 10 to the 4. Which is the same as square root would be 300, which is about right. Meters per second. This chair has lost its seal. And so if you're doing the calculation, this modulus is in newtons per meter squared. And this magnitude has to be in kilograms. These are our kind of standard units. You can check the units to make sure that they do come out to meters per second. But this is 300 meters a second. The conversion between meters per second is that I just know this, you don't need to know this, 1 meter a second is about 2 miles per hour. Another useful conversion. So it's about 600 miles an hour. And so that was what we used last time for me to make the comment that if you see a lightning bolt and it hits the ground and you hear it 6 seconds later, then that's basically 1 mile. You can do the conversion between 600 miles an hour, which is what this would be. And that would tell you something about how quickly the sound would travel in air. So those are shear waves. Those are what would be referred to as body waves within the atmosphere. The other kind of wave that we have is the celerity wave, which occurs in with a free surface, which is different from these. So you need to make sure that you understand that. What you're listening to me is a body wave that you hear coming through air. There is no free surface in this room. It's not half filled with water and half filled with air. But the celerity wave is something that occurs on a free surface. It's the waves that you see in a river or in the sea. And again, like the P wave, the analogy being hitting a train from the back and having the energy end up boom, 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 boom at the front is the same with a wave. So the wave, the particles of water that are moving here don't end up going down and causing this disturbance here. They're just physically rotating in space. And it's the energy which is transferred from one to the other. The particles essentially stay where they are, but the energy is transmitted. And I won't go through the calculation here, but the velocity of the celerity wave, as it's called, this is here. This is the spelling of celerity wave. For all intents and purposes in this class, we'll use the shallow wave equation, which is this. We actually derived it last time, if you remember. We derived it from Bernoulli equation. If you remember, we took the elevation, and we took the pressure head, and we took, whoops, the velocity head. We divided these two together, and we ended up with, if we do that, we ended up with v squared over 2g 1 over z, just by dividing these two together, one by the other. And that's the same as v squared over 2gz. And if we take the square root of this, which we can, we end up with v over 2gz. So here, this is the magnitude that we have for this wave. We don't have a z in this, but this is the velocity at which the fluid is traveling, and this is the velocity of the celerity wave. And it's important to us because, you know, when you're driving a boat or a ship through the water, it creates its own wave. The velocity of the ship is this. The velocity of the wave that is formed relative to the ship is controlled by the planet you're on, gravitational acceleration, and the depth of water. This z is just the depth of water below some datum. And so the only thing that controls the magnitude of the wave is this. So in other words, this is the velocity of a shallow water wave. So we can calculate that. So if we did that for the example that we're going to do, if we take the fact that on this planet, gravitational acceleration is roughly 10 meters per second squared, and if we work on a depth for the example we're going to do of 1,000 meters of water, then we end up with, for this, 10 times 10 to the 3, which is in meters squared per second squared. If we square root it, then we have something of the order of, this is 10 to the 4, same as 10 to the 4, square root 10 to the 4 is 100 meters a second, which is actually quite surprising, right? So we've said that the speed of the sound in air is something like 300 meters a second going to you. Sounds quite reasonable. You hear things quite quickly. It's strange to think that in 1,000 meters of water, a wave, as it travels, should be going at something like 100 meters a second. But it is. You can measure those, I guess with the caveat, of course, that it's 1,000 meters deep. So it's not at the shoreline where it'll be going slower. And so we can look at all of these individual wave speeds to be able to say something useful about a system that we'll talk about. The first is that the wave speed in a liquid and in a solid are quite fast, thousands of meters per second. The wave speed in a gas is a little bit slower, maybe by a factor of 10. 300 meters a second instead of 1,000 meters a second, but still quite fast. And the surface wave in a liquid, which is really what we're talking about in this class, is actually still quite fast. And so we can use these to look at this one particular example that I want to look at. I've actually spent more time on this than I wanted to. And that is, go ahead.
What did you get the velocity?
Say it again.
What did you get the velocity on that?
Where do I get what from?
Velocity. Divide square root of 10 times 10.
This is from the acceleration due to gravity, which is this, and the depth of the water, which I've taken 1,000 meters.
Right. We should divide that by velocity, right? So that means over the square root
No, I'm using this.
of the
The v is just how we got this ratio last time. This is the equation for the wave speed. The equation for the wave speed is equal to g times h square root. That's what we're doing. Yes? Go ahead.
So last in the reference, how much can we up
Can you speak up, please?
I mean, so after you mentioned in the water, you said velocity is 1,000 meters per second.
There are two different kinds of waves. There's a wave which is a compressional wave, which if you're underwater talking to someone, they would hear you. There's no free surface involved. There's also a surface wave, which is what you see at the ocean, at the beach, which is how quickly a disturbance travels on the surface. They're two different wave fields. Okay?
It's not just by calculation, isn't that goes faster than in the ground?
Say it again.
Okay, so just as you wrote, it's like square root of 20 times 10.
What's the square root of 20? Yeah, you have to speak up if you want me to answer your question.
Isn't that sort of like 4,000? Is that 1,000?
Square root of 20?
That's more about the calculation.
Square root of 20 is about 4, right? 16 is 4. So yeah, that was this one up here, right?
It's just cross it.
This is the square root of 20. You talking about this equation here?
Yeah.
Yeah. And so, yeah, so it's of the order of, I just dropped, I guess it should be 10, right? Because I got rid of the 2 here, and I got rid of the 2 here. And so it should be square root of, oh no, that's not right. So, well, do the well, I'm not sure. So if you want to, if we really want to go through this, the speed for water is of the order of 1,000. What are you disputing? Just the calculation?
So if that's saying the wave vector travels faster in the water than the rock.
No. So the modulus, I think I said that this is not 10 to the 10, this is 10 to the 9. So that's what changes it. If it's 10 to the 9, then this becomes 2 times 10 to the 6. This becomes 1.4, the square root of this becomes 1.4 times 10 to the 3, and this is about 1,400 meters a second, which is about right. Okay? All right. So the way that this can be used is that certainly the speed of sound in rock is relatively fast compared to the speed of sound in water or of the celerity wave. And so one example of this is the Tohoku earthquake in March of 2011. There's an earthquake about 100 kilometers offshore, which is about on the trench, which is on the east side of Japan. It's about 100 kilometers to get to the shore from here. And so one way of early warning is to have ocean bottom seismometers that sit on the floor next to the earthquake. They feel the earthquake immediately because the earthquake is right there, and they transmit the signal on land. So the signal gets transmitted electronically by speed of light, and so it comes on land essentially immediately. So that allows you to have an early warning for a wave to travel in. If we know this wave is traveling in at 100 meters a second, and it's going in at 100 kilometers, then we know that in 100 meters a second it will go a kilometer in 10 seconds, and it will go 100 kilometers in 10 to the 4 seconds, which is about 10,000 seconds. If you divide 10,000 by 60 seconds in a minute, what do you get? Roughly? Is it 14 minutes? I'll let you do it. 60 and 100 is 2. Yeah, so the order of 14 minutes. So in other words, you get some small amount of warning from a tsunami. You can also do the calculation for the wave speed due to traveling in the rock to be able to tell you how quickly, how much warning you'd have before this event hits you on land. So, is that right? It's 100 meters? 1,000 seconds equals 16 minutes. Good. All right. Thank you. Good enough. So you get 16 minutes warning of a tsunami. So I say that because I guess I'm not sure I'll have time to do that here because I haven't put that on yet. If we start this, put it on 0. So this is a video of Japan. March 11th of 2011, of some people standing on the top of a parking deck. Presumably they're on the parking deck because they just went there because they've just been shaken. Interestingly enough, in this tsunami which killed 2,000 people, 0 people essentially died in the earthquake, in the shaking of the buildings, unlike in Aguila, which was a very shallow earthquake, very close to, right underneath the town. And so now we can look at how much lead time we have if we know what we need to do. And of course what we need to do is find a tall structure to get on, which is like a parking deck, which is where this movie's been taken. So I don't plan to watch this for 16 minutes, but I think if you remind me in 5 minutes, we'll come back to this and see exactly where we are in terms of the progression of this. So you get some warning. You can also use that warning because there's some finite time between a shaking event happening at some remote location and those waves hitting you. You can calculate what the time would be. It might be a factor of 10 different. It might be a minute and a half just from the scaling of the different seismic velocities that we've talked about. And so if you go to Japan, this is actually in Tohoku, which is close to this earthquake. I guess, did I get a picture of this? Yeah, I did. If you look at this, I imagine you can get apps on your phone these days. This is 2012 in one of the buildings in the towns close by, Tohoku. This is just an early warning detector. Earthquake occurs offshore. Ocean bottom seismometers pick it up. They say, oh, that's a big earthquake. Signal goes on land, speed of light. The signal from the earthquake is traveling at the speed of sound in rock, which is 3,000 meters a second. And you get from that a factor, something like a minute and a half warning to be able to get out of the building and save yourself, basically. And so this is the effect on that same building. This is very Japanese. They outline all the cracks that they're going to repair, but actually it wasn't such a big event. Even though it was a magnitude 9 earthquake, it was far enough offshore and far enough away that there wasn't so much damage. I think one building on this campus was condemned. But the rest of the problems, all of the problems in this particular event were the earthquake, the tsunami that came from the earthquake. And so seismic velocities tell us something about the rates at which these events will move. All right. Those are wave speeds. Viscosity. Viscosity is the second parameter we'll talk about. What we'll use is Newton's law of viscosity. Newton's law of viscosity says that shear stress, which we'll call tau, is equal to a term called viscosity multiplied by a change in velocity in the x direction with y. And so the easiest way that we can demonstrate this is to think of two plates with a liquid between them. We pull a force on this plate so that it travels at some velocity in the x direction, Vx. And we hold this bottom plate static. If we look at the velocity profile of the fluid which is traveling with this top plate, it will look something like this. This is the x direction. This is the y direction. And if we just look at the separation between these plates as being y, then basically that defines all of the forces that we have, all the components we described here. So this is how the velocity changes as we go in the y direction. So if we were to write this out in full, this would be viscosity. What would be this term? This term would be this value Vx at the top, and it changes over a length y. This is just the thickness of this plate. If you want, we can call it y0. And so what this says is that if we want to pull this plate at the top at this velocity, and the separation between these two plates is some distance that we know, then we have to apply to this a force F, and that force we can translate into a shear stress, which is equal to tau, which is equal to the force that we apply divided by the area over which it's applied. And so the area of this plate, if you like, if you draw it out in 3D, this would be the area that we applied. So in other words, we have to apply, you can think of applying a stress to this plate of some magnitude tau, or you can imagine applying a force to it, which is distributed over an area of the plate, which is A. They give the same result. And so the point is that this term mu, which is the viscosity, is the term that controls how viscous something is. So water, we know gases are not very viscous at all. We know water, if it's flowing down a slope, is quite viscous. We know that treacle flowing down a slope is more viscous. It's the property that gives it that velocity. And so what we can do is if we measure a velocity by applying a force, the only thing we don't know is the viscosity, and we can measure the viscosity of that particular fluid. And so a viscometer, if you like, is just exactly that. Yes, sir? Pardon? Thank you. Good point. I like this guy. Has the video gone away? Does it need to refresh? 6.7, you were late. Nothing yet. Thank you. Yeah, I think that's the only reason for them to be up in the garage, right? They're taking the video to document it. I don't know that for sure, but that's my guess. Educated guess. Maybe not so educated. Okay, so 5 more minutes. So in other words, what we can do is, as a function of this, if we wanted to, we could also check the units for this. We did it last time. If we want to know what the units of viscosity are, we could take the units, we could just rearrange Newton's law of viscosity, which is what this equation is. If we rearrange it in terms of viscosity, we get this. We talked last time about units of pressure, which are the same as units of stress, which we derived from Newton's second law, right? F equals ma. So the units of pressure or stress are this. The units of velocity are length over time, and the units of length are this. And we could find out that the units of viscosity are in mass, length to the -1, t minus 1. If you actually used units instead of the actual mass, length, time indices, you'd find out that for viscosity, the units are Pascal seconds, which are the same as newtons per meter squared times seconds. And so you can always check exactly what the material, whether your calculations are right by checking the magnitudes of the units. Viscous fluids come in a variety of different forms. The ones that we'll talk about are Newtonian fluids, which have a linear dependency of this velocity change, we've called this dvx dy, with the stress that you apply to it. So if you apply a certain stress to it, it will move at a given velocity. If you double the stress that you apply to it, it will double the velocity at which the plate moves. It's a linear system. There are other fluids, such as non-Newtonian ones, which don't behave in the same way, and there are plastic fluids, the best example of which is thixotropic fluids, which are drilling muds, which if you leave them, they're just a suspension of bentonite and water, which if you leave them, they appear like a solid. You have to provide a certain finite shear strength before you get it moving at any velocity whatsoever, and then above that, they're kind of linear. And so those are particularly designed that way so they don't seep into the formation and you lose them all. Okay? So you can use, if we look at the materials that we're dealing with, the viscosities of water, typically the viscosity of liquids reduces as you increase temperature. So this is temperature versus viscosity. Viscosity on the left axis. A typical viscosity for water is of the order of 10 to the minus 3 Pascal seconds, newtons per meter squared seconds. And the property of gases is that different from liquids, as you increase the temperature of a gas, it becomes more excited and the viscosity goes up slightly, although this is quite flat. Okay? So there's an example problem here. You can look at last year's video if you want to see how to do it. It's basically asking the question of if you apply a force to this of 29 newtons, and as a result of this, this goes through this plate sandwiched between a fluid 1 on the top and a fluid 2 on the bottom. What is the viscosities of those fluids? Well, you could draw yourself a little velocity diagram that says on this plate we're pulling ourselves at velocity is equal to 0.3 meters a second. If it's anchored at the top, then that velocity has to vary linearly down through here. Likewise, in the lower fluid, the velocity through this has to be going at the same velocity here. And you could just write the equation, the shear stress applied on this plate is going to be the viscosity of fluid 1 multiplied by the velocity, which is equal to 0.3, divided by the length over which that occurs. And I don't know what that length is, but it's somewhere in the problem statement, this length here, divided by L. And also, there's a force due to the one in the bottom, which is going to be equal to 2 times viscosity 1, multiplied by the velocity, which is equal to 0.3 meters a second, divided by the length over which it occurs. You know the velocities, you know the lengths, you don't know this viscosity, but you do know the force that's applied on a unit area, which is equal to a force over an area. If you know this force, if you know this area, then you know everything in this except for the viscosity. And so you can get it. 5 minutes, thank you. Let's see if we get this. Why does it do that? 11 minutes and 43 seconds. Boats going out to sea. Smart thing to do, right? In a storm or in a tsunami. Okay. Back to more fluids. Okay. All right, so viscosity. So the working is there, so you can check that yourself if you so wish. Vapor pressure. Vapor pressure. So we talked a little bit of time about phase diagrams. Vapor pressure, of course, is when a liquid turns into a gas. An example of this is the vapor pressure diagram here for liquid water. We know we sit at 1 atmosphere. We know that at 1 atmosphere, the freezing point of water is 0 degrees centigrade, which is this point here. We know that the boiling point of water is 100 degrees centigrade, which is here. And so if we heat up water, then ultimately we go from liquid to a vapor. We know also that if we cool it down, then we can freeze water here. We also know that if we change the pressure in some way, then what will happen is if we go, say, from room temperature here down to here, then water will actually boil at a temperature which is much lower than 100 degrees centigrade. And so that's important because it defines exactly how you can cavitate water. So in other words, you could, at room temperature, boil water just by reducing the pressure. And so a practical example of that is if you look at the blades on submarines, for instance, the low pressure that you get on the top blade of a screw that drives a submarine, is dropped to a low pressure. If as a result of that, the water boils and becomes a gas rather than liquid, what it will do is it'll just pull off chunks of the metal over time that will destroy the propeller. It'll also, if you're using a sub to actually kind of sneak around in the deep and not be heard, it will also make bubbles that will be heard. And so it defeats the object of being available and around. So the other question that comes from this is what happens if you go up onto Everest? We haven't talked about, you know that if you go up in a plane, the pressure reduces as you get up to 35,000 feet. Then that's exactly what you're doing as you're going down here. So in other words, if you look at being on Everest and trying to boil water, water will boil at a lower temperature. And at that lower temperature, then it will take longer to cook something, because to cook something it has to be exposed to some certain temperature for some reasonable amount of time. So if it boils earlier, the water might be only 80 degrees centigrade. If it's 80 degrees centigrade, then to cook something at 100 degrees for 5 minutes might take 10 minutes to cook at 80 degrees, etc. And so water can exist in two different states, and we should know that. Are we up 5 more minutes yet or not? Might want to check. 14 minutes. Don't think so. It's still running, right? All right. So we're right at 14 minutes. That was our calculation. We know certainly the event could have happened before this. Otherwise, there's no reason to be up on the parking garage. But it could have, the recording could have started later. So it's at least 14 minutes in, I would think. Okay. All right, the final topic is interfacial tension. So surface tension is the idea that a liquid has an interface with the gas, and on that interface there's some tension that's applied. The manifestation of it you see is bugs walking on water, which is the reason that insects can walk on water, because their feet have some pads and the force applied to their feet allows them to be suspended. The other manifestation of that is if you take a capillary tube and you dump it into water, if you take a small tube and dump it into water, then there'll be a rise of fluid within that capillary tube, which will be higher than the location of the free surface, this value h here. Depends where you want to take this value here. I guess we're taking it at this value here. And so it depends whether the fluid that you have is a fluid that loves glass, in this particular case, hydrophilic, in which case it will try and climb up the glass and out, or if it's hydrophobic, in which it hates glass and it doesn't want to have any contact with it, in which case it will be depressed. So if you put a glass tube into mercury, you'll get a depression, but it's due to exactly the same process. The mercury doesn't want to have anything to do with the glass it touches, and so the surface tension that acts here can be thought of as a force that's pulling it physically down in this direction. So if you want to calculate the rise that can occur of this, all you need to do is realize that atmospheric pressure acts on this surface. We can cut this thing off at atmospheric pressure. And if we do that, we can make a little free body diagram that looks like this. And we can resolve the forces that are acting in both directions. So we have two forces. We have the weight of this acting downwards, which is the mass times gravity, which is equal to its volume times density of water times gravity, which is equal, if this is height h and diameter d, bless you, is going to be equal to, its volume is pi d squared upon 4 times h, right? This is volume, this is density, and this is gravity. Okay? The forces acting upwards are the interfacial tension, and it occurs on the circumference. So the force acting upwards is equal to pi d, which is the circumference, multiplied by interfacial tension. And so if we equate this force to the weight of the fluid, then just by writing these two expressions, pi d times interfacial tension has to be equal to this term here, which is pi d squared upon 4 times the height times density times gravity. I think we can get rid of some terms. We can get rid of a pi, we can get rid of a d, and if we rearrange that, we end up with the height rise, which is this one term here, is equal to the interfacial tension divided by times 4 divided by rho g, which is the same as 4 times the interfacial tension divided by the unit weight of the fluid. A simple relationship. So it may seem an esoteric thing to talk about. Why do we care about tubes that have fluids rising in them? Well, tubes are often used as an analog for porous media. So if you look at pushing oil through an aquifer or a reservoir, or contaminants, multi-phase contaminants through a reservoir, through an aquifer rather, then the fact that you have two phases present means that you have maybe water, and instead of this other liquid here, other fluid here being air, it might be hydrocarbon. And so it says that the height rise that you get is proportional to the interfacial tension. Oh, I've left out a D, right? No. Where's D in this? Thank you. So the height rise is proportional to the interfacial tension, and it's inversely proportional to the capillary diameter. As you get a very high capillary diameter, small capillary diameter, you get a very large height rise. That translates to the fact that if you have Marcellus shale, you can't get oil out of it very easily unless you apply a very big pressure. If you have a big open material, then you can. Hold on your horses there. "20 minutes. So this is just the breakout on a reef. This is the rise of sea level within here. Let me just shoot. And if you look to what's going on in this little inlet that is next door to them, then after 22 minutes, that's not a normal river that's going there. So if you keep on watching it, you'll see. So basically, tsunamis, they're called, the Japanese word tsunami means harbor wave. It's not really a crashing wave, but it's just a constant rise in sea level with a very, very long wavelength that goes out to sea that ultimately stays in place and causes a very large water level rise at the coast, which then pushes inland relatively slowly but inexorably.